Now that we already understood which type of nuclei will undergo which type of radioactive decay and already studied the emission, what are the properties of the emission, now we'll move on to study the process of the radioactive decay itself. So it means that we're going to study how fast it happens, what does it depend on, those kind of relationship to understand the radioactive decay. So first of all, radioactive decay, you have to understand that it is a random process and at the same time it is a spontaneous process. So let's go through the idea, what is random, what is spontaneous. So random, the word random means by the time of decay of each nucleus cannot be predicted. Means by if you are focusing on one single nucleus in the whole material, that you focus on one single nucleus, there's nothing that you can do to predict when will that particular nucleus decay. Okay, usually when let's say if you are looking at a student answering exam, you can predict how fast the student will finish the paper because there are things that you can observe, means by the speed they are writing or how good is their understanding of the knowledge. There are things that you can observe in order to predict when will the student finish the paper. So in that case, those kind of process, we call it not random. Okay, there's some you can predict when it can happen. Okay, but when you talk about radioactive decay, if you look at a particular nucleus and you want to predict when will that particular nucleus decay, it is impossible to be done. There's nothing that you can observe. You cannot look at the temperature, you cannot look at the pressure, you cannot look at the kinetic energy. Those things won't tell you when will the nucleus decay. Okay, there's nothing that there's no information that you can use to predict the decay when will it happen. So that's the idea of random. You cannot predict when each nucleus decays. Next, for spontaneous, the decay of each nucleus happens by itself without external stimuli. The decay is unaffected by normal physical or chemical processes such as heat, pressure, and chemical reaction. So the idea of spontaneous means by you don't need to do anything, it will decay by itself. Okay, the more suitable word is not that you don't need to do anything. There's nothing that you can do to make the nucleus decay faster or slower. You cannot control the process through external factor. You cannot heat up the material. You cannot soak the material in water, do some kind of chemical reaction to increase the rate of radioactive decay, and those things are not possible. When it wants to decay, it will decay by itself. You cannot do anything from external. You cannot do anything externally to affect the process, to speed up or slow down the process. There's nothing you can do about it. So therefore, we can say that for spontaneous, it means that you can't influence when each nucleus decays. So you cannot predict because the process happens by random. You don't know at which moment which particular nucleus will decay. Then it's spontaneous because you cannot do anything to change the rate of the process. So that's why we call radioactive decay being random and spontaneous. Okay, so here is an example of radioactive decay. We have actually studied this reaction. It's an alpha decay, in which you have uranium-238 undergo alpha decay to become 234 thorium, releasing a helium nucleus, which is also known as an alpha particle, and some amount of energy. So in this case, we are going to call the nuclei that we have before, or you can say the nuclei we have initially, we are going to call it as parent nucleus. Okay, if it's plural, then parent nuclei. Then the product over here, okay, we are going to call it as daughter nuclei or daughter nucleus. Okay, so parent is the one we have initially. The result, we are going to call it as daughter nucleus. So the helium nucleus over here, even though it is a product, but we are going to call it as emission. So it's going to call alpha emission, or you can call it as alpha particle, alpha decay, but it's emitted means that it's no longer staying inside the block or your material. It is emitted to the surrounding. Okay, then this is energy. Okay, so if you focus only on the parent nuclei and the daughter nuclei, you should imagine the process to be something like this. Initially, you have a material which in this case is made of 100 parent nuclei, because they're in purple, they have 100 parent nuclei. But you cannot predict when each of these nuclei, when each of these nucleus will decay, and you cannot do anything to make the decay rate faster or slower. So what you're going to do is you are going to just observe and see when will the decay happen. But at some point in the future, you should expect that there will be many parent nuclei will undergo decay and they are now becoming the daughter nuclei. So you can see a big portion of the purple color, parent nucleus, parent nuclei has already changed to become daughter nuclei. This process initially it happens quite rapidly. You can see quite a lot of parent nuclei change to become daughter nuclei. But as time goes on, you are left with less and less amount of parent nuclei. Okay, because many of them has already decayed, so what's left that haven't decayed will be getting lesser and lesser. So if your parent nuclei gets lesser and lesser, you should expect less decay will happen as time goes by. So initially there's a lot of decay that happens, but as time goes by, you see less and less decay happen. The decay gets slower and slower as time goes by. So you can see even though initially it drops severely, there's 63 nuclei that decays. Afterwards you can see from 37 to 17 means there's only 20 nuclei that decay. Afterwards there's only 12 nuclei that decay. So the decay rate will get slower and slower because the number of parent nuclei available to be decayed will get lesser and lesser. So if there are less parent nuclei that are available to be decayed, you should expect that at each moment the number of decay that happens will get less and less. So that's the idea we are trying to use to derive an equation later. Okay, so because the number of parent nuclei n decreases with time, thus the value of dn dt is negative. So if you want to study how does the number of parent nuclei changes with time t, you should see that the number of parent nuclei is actually decreasing. So this value dn dt here should actually be a negative value. Okay, so you should expect that the value of dn dt will be a large value at earlier times, but the dn dt will gradually get smaller and smaller when you reach a later time. This dn dt here is not a constant value, it should change during the decay process. Okay, throughout the decay process. Okay, so that's a rough idea of the nature of radioactive decay. So later we are going to take this understanding that we have over here to derive the equation to understand the rate of radioactive decay and how does the decay happens with time. Okay.